Okay, measurement. So we need to know how to deal with the measurements in energy management because we take measurements of various things. So some examples might be temperature of a room. We take air pressure in a duct perhaps. We might look at flow of water through a pipe. So all those are examples of measurements, and we need to understand how to work with them and how to understand them. So one important concept to understand is accuracy versus precision. And a classic example to understand that is a bullseye. So if I draw a bullseye here, and here. So imagine I'm throwing darts at this bullseye. If I'm very accurate, I'm going to be close to the mark. That's my true value. So I might have one here, 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 here. So that would be considered fairly accurate. But over here, if I have a high degree of precision but low accuracy, I might see a bunch of darts very concentrated in one area. So I'm very precise, but I'm pretty far from the bullseye, so I'm not very accurate. So on this side you have more precision, and on this side you have more accuracy. Of course, the goal is to have both. So if you had a high concentration in the bullseye, you would be both accurate and precise. And this concept applies to measurements. So some sensors, when we measure temperature, for example, will be very accurate but not very precise, or vice versa. So you kind of need to understand where you're getting your data from. Another concept we need to be familiar with is uncertainty. So some things we could consider to be certain, like if we're counting something. We're going to assume in this program that we can all count correctly. So counting is infinitely certain. So we have what's called infinite number of significant digits, or infinite number of significant figures in counting. We know exactly that number. But for measurement, we have some degree of uncertainty. We can never measure anything exactly. There's always some range or some uncertainty in the measurement. And what we're going to talk about next is how to communicate that level of uncertainty and how to work with it. So one of the most common ways we do that is with something called significant figures. Sometimes we call it significant digits. And the easiest way to start understanding how to do this is just looking at some examples. So if I have the number 3 and I have number of sig figs, 3 has one significant figure because it's just one digit there. So if I write 300 next, you might say, well, there's 3 digits there, so it's got 3 significant figures. But when we see a number written like this, the zeros have to be there as a placeholder. They're not necessarily expressing any more certainty. So this number actually has one significant figure, and that's the 3. If I wanted to communicate that those zeros are significant, I would write 300 with a bar over the zeros. Then I would have 3 sig figs. And I can do any combination of that. So I can have 3, 0, 0 with a bar just over the first 0. That means there's only 2. This 0 is significant, this one is not. It's just a placeholder. I could have 3, 0, 0 with a bar And again, I have 3, because if this 0 is significant and this 3 is significant, anything in between is also significant. So therefore, this 0 is significant even though it's not marked as such. Now let's go the other direction. If I have I'll do it over here. If I have a value of 0.3, again, this 0 is not doing anything except holding a place. So this is only one significant figure. If I said 0.30, the 0 doesn't have to be there. It's not holding a place. So I have 2 sig figs in 0.30. If I have 0.03, I only have 1 because that 0 is a placeholder. Now when I do scientific notation, 5.20 times 10 to the minus 4, as long as this number is written in normalized scientific notation, then I can just count the digits. So I have 1, 2, 3. The 0 here doesn't have to be written. If it is written, it means it's significant. So I have 3 significant digits. You don't have to worry about placeholders in normalized scientific because you would never write a 0 here. And you would never write extra zeros here unless they were significant. So one of the easiest ways to see how many sig figs are in a number is to convert it to scientific notation and then just count them. So when we say a value has a certain number of significant figures, it's telling us information about the precision of that number. So for example, if I have 300 here and it's only one significant figure, it means the number is 300 plus or minus. Now we look to the place after the last significant figure. So in this case we only have 3, so we look to the next place and we take half of that value. And we're going to have 300 plus or minus 50. So this number could be anywhere from 250 to 350, just under 350, and still round to 300 if we're rounding to one significant figure. So when we write 300 with no bar over the zeros, what it means is this. Let's do an example with the 300 with the bar. So that's our regular 300, and our 300 with the bar is equal to 300 plus or minus. Now again, we look to the last significant figure and we looked one beyond it. So this would be plus or minus 0.5. So the number could be 299.5 to 300.5, just under it. So hopefully you can see that by carefully looking at the numbers and the number of significant figures, we can see an implied tolerance or range to the numbers. Okay, let's talk about rounding. Sometimes you'll get a result or a measurement and you might have a number like 12.3456. And in a homework assignment, I might ask you to round this number to 3 significant figures. So currently this number is representing 6 significant figures, which in general is way too many. Usually 3 is as far as we go in this field, because if you think about it, if you're beyond 3 sig figs, you're talking about changes of less than 1 part in 1,000 or 0.1%. So often we only go to 3 sig figs. So if I do that for this number, I would write it as 12. Now should this number be a 3 or a 4? To check that, you look just one place past it. The 4 is less than 5, therefore I round this down to 3. So my answer would be 12.3. A common mistake that I see students make is to try to round every digit from the right and moving left. So they would round the 5 to a 6 because 6 is greater than 5. And they would round the 4 to a 5 because this 6 would be still greater than 5. And then they would round this 3 up to a 5, or excuse me, a 4 because, so let me show that in action. 12.346, 12.346, 12.35, and finally 12.34. Excuse me, 12.4. So this is the wrong way to round. You don't round successively from the right. You just look one digit past where you want to go. So you look to the 4 only. You ignore this other stuff. So this is the wrong way. Now one thing that's kind of tricky to understand is how to do math operations on numbers and keep track of sig figs. So we're going to start with multiplication and division because those are actually the easiest case. So if I'm dividing or multiplying two numbers, let's say I have A is written to 3 sig figs and B is written to 2 sig figs. Then A times B will have 2 sig figs. And the reason is because the answer should be as precise as the least precise number that you start with. So because B only has 2 significant figures, A times B is limited by that and it will only have 2 as well. And this applies whether you're multiplying or dividing, same thing. So let's do an example. If I have 24.8 times 500, this number is written in 3 sig figs, but 500 only has 1, because remember there's no bar with zeros. Therefore, well, I calculate the answer to be 12,400, but then I have to convert that to 1 sig fig. So I look at the 1 and 1 digit past it, I round that down. So I end up with 10,000. Now let's do another example, which is example 3 in the notes with eggs. So I have 12 eggs. Each egg has a mass of 52.3 grams. So the question is, how much does the entire dozen weigh? Well, I multiply 12 by 52.3, and you should get an answer something like 628. This is rounded. Why do we round to 3 sig figs? Because there's 3 written here. The 12, if it was a measurement, would only have 2 significant figures, but because it's counted, right, there's a dozen eggs, we've counted them, so it's infinitely precise. Therefore, the counted number does not limit our number of significant figures. Only this number does. So the answer would be 628 grams. Now, one important point to make is that if you're doing multiple multiplications and divisions, you should carry all the digits forward to the very end before you do any rounding. Don't round at each step. If you do that, you'll get errors that will compound themselves. So continuing with our math operations, next we'll look at addition and subtraction. And this is actually a little bit more complicated to keep track of the significant figures. So the easiest way to see this is with an example. Let's say I've got 12.34 plus 4.5. So if either of these numbers had been written in scientific notation, the first step would be to convert them to normal format like I've written here. But since they're already there, what we're going to do is line them up just like we did in grade school. 12.34 and 4.5. You line them up with the decimal point in a single column. And then what you do is you circle the guess digit. So when we have numbers written with a certain number of significant figures, the rightmost significant figure is the guess digit. So in this case, the 4 is my guess digit. I'm going to circle that. And in 4.5, it'd be the 5, so I'm going to circle that. Then I perform the addition. $16.84. Now, the result can only have one guess digit because each of the components only had one guess digit. You're only allowed one guess digit ever. So I have one guess digit in this column, and I have one guess digit in this column, and no guess digits here. And I have to have one guess digit. So I go to the rightmost column that doesn't have any, which is the 2 and the 4, and I go one past it. So this would be my cutoff point. My 8 is my guess digit in my new number. So I round to that spot, and my answer becomes 16.8. So the 4 gets dropped. Let's do one more example. 7.6 plus 1.2. Circle the guess digits. That's the 6 and the 2. I perform the addition. 8.8. Now in this case, my guess digits are in the same column. Therefore, my guess digit is that same column in the answer. And I don't have anything to do. My answer is just 8.8. So you can see there's only two possibilities. Either the guess digits are in the same column or they're not. If they are, then you don't lose any numbers. You don't have to do any rounding. If they are not in the same column, you take the one to the left. That becomes your guess digit place for the answer. So just do a few of these to practice, and it won't be too difficult. But it's a little bit more work than doing multiplication and division. You actually have to write it out like this. You can't just punch it in your calculator and know how many figures to round to. You have to look at the guess digits. Okay, I want to say a few words about why we use sig figs. Basically, the reason it's important to know this stuff is because you don't want to over communicate or under communicate. I should say overestimate or underestimate your numbers. So if you write a number, that you got in your calculator result as 123,456,789, and let's say that's in dollars. What you're saying is that you know this number to the nearest dollar, essentially. And you've got 9 significant figures. And I can tell you that you almost never have that many significant figures in anything, unless you're a physicist and measuring things to that level of detail. It'd be much more likely that you would have a value of 123 million. So the cost of some project to the nearest million, even that is difficult to estimate. But this looks much more sensible than this. This, you're communicating way more information than you actually have. You don't know these numbers to the nearest dollar. So sig figs is a way to keep track of that and a way to communicate that to other people. But in practical purposes, we often ignore this issue in classes in this program. So I'm only going to ask you to understand these concepts for the first homework assignment, which is homework 1. So on Moodle, for homework 1, your answers have to be exact. There's no plus or minus 5% like last term. You have to get the exact answer, and you have to put all your answers in scientific notation. There's a help file on Moodle to show you some examples of how to do that. So homework 1, you have to worry about sig figs. After that, you don't have to worry about sig figs anymore. It's just too much of a headache. So after that, the Moodle quizzes will go back to the plus or minus 5% tolerance like we had last term. So for homework 1, be very careful with sig figs. Put your answers in exactly. And after that, we're going to do just the plus or minus 5% tolerance like we did before. And remember, don't put units. I should also mention that in Excel, it's also possible for us to look at sig figs. Excel keeps track of as many digits as it can internally. Whether it displays them to you or not depends on your settings for that cell. Unfortunately, Excel only lets you easily control the number of digits after the decimal point. So if I have a number like 8.305 and I change it to 2 digits after the decimal point, it doesn't mean 2 digits of significant figures. It doesn't mean 8.3, it means 8.31 because it only looks after the decimal point. You can tell Excel to display numbers with a certain number of sig figs, but it requires a lot of work and formulas, and we're probably not going to get into that in this class. So this sig fig thing, it's just something I want you to be aware of. When you get out in the real world, you should keep it in mind. It looks much better if you have a figure written like this than like this. If I see this in a report, it tells me they don't understand anything about significant figures, and they sort of may not know what they're talking about. So, even though we only enforce this for one homework assignment in this class, it's still something you should keep in mind for the rest of your career.